defensive back pursuing a ball carrier needs to pick an angle for the pursuit. How can they know which angle to take? And is there a way to know if they're on track to make the tackle during the pursuit? If they aren't on track, what adjustments do they need to make to still be successful? In this video, we'll develop some techniques for the defensive back that are actually usable in the heat of the game, not just when we are armchairing and have a computer to help with the calculations. Welcome back to Math the World. In this video, we are analyzing the mathematics of pursuit from the perspective of a defensive back trying to catch a ball carrier. Let's set up the problem similar to the truck evasion problem. We have a distance from the defensive back to the sideline. We'll call this distance L. We have the distance downfield from the ball carrier to the level of the DB. We will call this distance D. Let's also assume that the speeds of the two athletes are roughly equal. We'll call those speeds S. In previous videos, we built a similar mathematical model for these evasion and pursuit problems. We looked at which angle maxed out this function to help a pedestrian know which angle to take to have the best chance of avoiding an oncoming truck. But in that situation, we tried to maximize the time between the person and object getting to the same spot. But the defensive back wants this time to be 0. They want to arrive at the edge of the field at the same time the ball carrier gets to their position. So the defensive back isn't looking to maximize this equation. They're looking for the direction that makes it so their time to get to the sideline equals the ball carrier's time to get to the defensive back. Or in other words, what angle makes this function 0? We've assumed that the two athletes have the same speed. We learned in the previous videos that the relative speed is all that matters, that the distances didn't matter at all in determining the optimal angle for evading the truck. But is this true for the DB problem? Notice when we start solving for x, we're able to eliminate speed from the equation as a first step, but then quickly get stuck in solving the equation. Since our speeds are no longer in the expression, they don't matter in determining the best angle for the DB, but the distances are still in our equation and do seem to matter. This equation is beyond the solving techniques we learn in school. If we have Wolfram Alpha help us, then we can find an expression for the solutions given our two distances, but the solution is crazy and not easy to interpret. This expression inside the inverse tangent function is a little helpful. From it we can tell that if D is about equal to L, meaning the distances from the sideline and the distance down the field are approximately the same, then the optimal angle is 0, so running perpendicular to the sideline is the best option. But we didn't need an expression to tell us that. We can get that from geometry. If the distances D and L are the same, then both players are equally distant from this spot, and they're going the same speed, so yes, that is where the DB should run. Our current mathematical model might not be much more help to us in this football problem. So let's move to a geometric model. It might teach us something about the situation that we can actually use to help coach DBs. If the two runners are the same speed, then they cover the same distance in the same amount of time. So one strategy is to find a point on the sideline that is the same distance away from both the DB and the ball carrier. The set of all points that are equal distant from these two players is a perpendicular bisector of the segment between the two players. We can draw this line segment between them, construct the perpendicular bisector, and where it intersects the sideline is the place the DB should run to. This is the soonest the DB can catch the ball carrier, again assuming that they are the same speed. This gives us the first rule of thumb for the DB. Visually estimate the perpendicular bisector of the two players' positions and go to where it would hit the sideline. In the heat of the moment, this will have to happen very quickly. Does it matter if the estimate is off one way or the other? We learned in previous videos that in the truck evasion problem, it didn't matter much. Being off by a few degrees made the same difference whether it was lower than the optimal angle or larger than the optimal angle. But here, it matters. There's no leeway for the DB if he runs too far upfield. He will miss his chance for the tackle, because the ball carrier will be past him by the time the DB gets to the sideline. So it's much better to err on running down the field. He might give up an extra yard or two, but that's better than not getting the tackle. Remember that this path is based on our assumption that the players have the same speed. If the DB is not as fast as the ball carrier, then he will need to run further downfield. On the other hand, if the DB is faster than the ball carrier, then he has some cushion and doesn't need to err on running down the field. One way to think about this isosceles triangle path is that it is the riskiest of all possible paths. It's risky because if estimated a little too far upfield, or if the ball carrier is faster than the DB, then the DB could miss the tackle. But if the DB can make the tackle on this path, it keeps the opposing team at the shortest gain possible. It's high risk, but high reward. At this point, there are two intriguing questions. Is there a way for the defensive back to know whether he's on track to make the tackle during the pursuit? And two, if there's a riskiest path, is there a safest path? So let's turn to the first question. How should the DB know if he's on a collision course? The answer is by the swivel of his head. Let's assume that the DB is on the ideal path, the isosceles triangle path, and let's look at how the isosceles triangle made between the two ball carriers from the collision point changes as they run. A moment later, both players have traveled the same distance, so now the new triangle is this isosceles triangle. A moment later, it's this isosceles triangle. All of these are similar triangles, so this angle stays the same during pursuit. That means if the DB is watching the ball carrier, the rotation of his head won't change as long as he is on the ideal path. We can see this on the video clip. The angle between the head and the shoulders seems to stay constant right up until the moment of contact, showing that the DB was quite close to the ideal path. With this information, we have now figured out something that is really useful for DBs in the moment. Even if they don't use the geometry to initially pick a direction, they can pay attention to the swivel of their head as they run. If they're running in a straight line and their head doesn't swivel while they watch the ball carrier, they are golden. If their head swivels backwards, they're going too far downfield. If their head swivels forward, they're heading too far upfield. Here's an example of bad pursuit, because the head is constantly moving downfield, showing that the player is not on a collision course. The head swivel strategy is extra powerful because it doesn't rely on the assumption that both players are the same speed. No matter their speeds, this strategy still works, because the triangles formed by their distances are still similar triangles. This fact is one coaches can use in other sports as well. How can baseball players know if they're on track to catch a fly ball? Well, if players always run so the rotation and elevation of their head doesn't change as the ball comes down, then they're on a collision course with the ball. So we figured out two helpful strategies for a defensive back. First, they can use the perpendicular bisector to find the isosceles triangle path, the direction to take for the earliest possible tackle. Granted, this is a risky path. Poor estimate can cause the player to miss the tackle, which brings us to our next strategy. They can pay attention to the head swivel during the pursuit and use that to adjust their direction. Even if the DB just uses intuition to pick an angle, they should pay attention to their head swivel in order to adjust their angle as they run. This way they stay on course for the tackle. Hockey players chasing down pucks or soccer players chasing down balls or players can use the same strategy. What if a DB doesn't want to take the riskiest path but wants to take the safest path? There is another path we could call the safe path. Let's go back to the mathematical model we developed in the truck evasion problem. This function takes an angle as an input and has time as the output. The extra time the DB would wait until the ball carrier got to his position. We used this model to find the angle a pedestrian could take to give them the most time to evade a truck. Taking the same approach doesn't help here because if the DB and the ball carrier have the same speed, then the model says to go straight down the field and not run towards the ball carrier at all. Following that strategy is going to get that DB pulled from the game immediately. So let's take a different approach. If there is a possibility of the DB catching the ball carrier, there's probably more than one path the DB could take. There's this optimal path that maximizes the time between getting to the sideline and the ball carrier getting to the DB, but in most cases, the DB could also catch the ball carrier by going a little one way or the other from this optimal path. So if there is a possibility of making the tackle, there are probably a lot of paths the DB could take. These paths are represented by the angles that make the value of our function positive, because that means the DB would get to that spot with time to spare to make the tackle. Any angle between these two paths is a viable angle to take. But depending on the distances involved, that set of angles could be large or small. How can the DB know which angles may lead to a tackle, or is there a way to always find at least one such angle? Let's move the ball carrier down the field. As we do so, it'll be harder and harder for the DB to get to the ball carrier in time. Eventually, there will only be one solution. If the DB could find this solution, then no matter where the ball carrier is, this is the best chance to get a tackle. In order to find this path, we must ask ourselves, is there anything special about this path? Right at this moment, when there's only one possible angle to make the tackle, the angle the DB takes looks like 90 degrees. We can actually check this. We can show that this angle is 90 degrees using trigonometry by cutting the angle up into these two pieces. The upper part we can calculate with arctangent and these distances. And we learned in the previous video that this path is the arcsine of the ratio of the two speeds. Notice that they sum to something very close to 90 degrees. Here's one thing that might convince you that this claim is correct. In this animation, we have all possible angles the DB could take to make the tackle. We also have the perpendicular path. Notice that the perpendicular path seems to always stay in the interval of possible angles. This is quite a claim we're making, and a visual justification still might not convince you. So we provided a mathematical justification in another video linked below. So we now have a safe path the DB can always take. This path perpendicular to the line between the DB and the ball carrier. This is independent of speeds or position. This path will always be a direction that will get the tackle if there is any possibility of making the tackle. So let's recap where we are at. The DB can take the isosceles triangle path that gives the DB the chance for making the earliest tackle, assuming the speeds of the athletes are about the same. Or the DB can take the safe path, this perpendicular path, which works no matter what the speeds are. The isosceles triangle path is the furthest upfield the DB should go, and the perpendicular path is the furthest downfield. As long as it isn't past the goal line, then they can head for the pylon. No matter what direction the DB takes, he should pay attention to the swivel of his head as he runs in order to make adjustments. If the DB's heading in the perpendicular path and his head is swiveling downfield, he's too far out of position or not fast enough to catch the ball carrier anyway. After doing this analysis, I talked to one of our defensive back coaches here at BYU. He said that the angle the DBs take are very important and that they work on drills consistently to help players build a good intuition about what angle to take. He also said that DBs are trained not to aim too far upfield because one of the roles of the defense is to keep ball carriers along the sideline, where it's easier for the defense than to let them cut back into the middle of the field. That wraps up the football situation. We have a detailed justification that shows how the perpendicular path is always a safe path. It's in a past video, and you can watch using the link in the description. Thank you for watching. Please subscribe and share our videos. Be sure to follow Math the World on Twitter, Instagram, and Facebook. Thank you so much for your support.